Could have done that whole flippy doofer thing. Nope, where did I put the yellow box? Good afternoon, folks. How are we going? Just getting to that end of the day when we all still want to be here and do things and the energy wanes. So by all means, if anyone has any questions while I'm talking, feel free to jump in and let's make this casual and interactive, hopefully rather than being too dull. So really just what I want to spend a few minutes talking about today is the work that we're doing with the Serval Project and the intersection of that with OpenWRT. And so we're going to start with a little bit of background information around what the Serval Project is and why we actually have a need for OpenWRT. So really, the Serval Project is all about enabling people to use their mobile phones in disaster situations. And I think we don't really need to go over too much of recent history around the world to see that there are many situations where there is a need for mobile communications following disasters, whether they're natural disasters or whether they're disasters which unfortunately have been caused by the actions of other people. And sadly, I think we see more of the latter rather than the former of late. And so what we set out to do initially back in 2010 was to enable mobile phones to communicate directly with one another with absolutely no other piece of hardware. The irony of technical progress, of course, is that at the time we could do that by routing the early Android phones. We could use, the Wi-Fi driver had support for ad-hoc Wi-Fi, and so we built software around that process. Unfortunately, as I say, the irony of progress is that successive versions of Android have actually made that harder and harder to the point where it is now effectively impossible to get mobile phones to directly communicate with one another without going to tremendous lengths. Actually, one of the research groups at TU Darmstadt, where I'm based for the next few months, have been working on the Nexus 5 phone, reverse engineering the Wi-Fi firmware and adding back in the ability to do monitor mode and various other interesting things that could be of potential support. But this is extreme effort for one model of phone. So anyway, so really I guess what we're trying to let people do is to have text communications one-to-one, one-to-many, so SMS style and Twitter style. We'd like those communications to be secure where people would like it to be so. We would like it to be authenticated so that people know that the communications have not been interfered with in any way. So for example, if you're New Zealand Red Cross, who we've been working with, and you want to put out information about where food and water and supplies can be found, we don't want that information being tampered with by anyone along the way for nefarious purposes. And again, sadly, sort of the trend over the last number of years, and I think this is quite correlated with the increasing prevalence of human-mediated disasters, is that there are groups of people, organisations, in some cases even nation states, who are actively working to prevent humanitarian response. And I think if we look at what's happening in just the complete tragedy in Syria at the moment, we can see that there seems to be quite active work on the part of a number of parties right up to national level to prevent people getting aid in certain locations. So we're trying to find ways around these problems as much as we can. And to create all of this, we realised actually quite early on that IP is fantastic for the internet. Unfortunately, it's not so fantastic for networks which are ordinarily partitioned and where there is no central authority in any form. So the idea of even having a certificate authority in these kind of distributed networks is actually really hard to do, particularly if you require that the network can be deployed during a disaster. So the Serval Mesh app can be installed from one phone to another via Bluetooth or via Wi-Fi, just transferring the APK across, and then each new installation can set up. It doesn't require to even connect back to the internet even once for that to happen, because otherwise it would be useless for our use case. And so this has really kind of created really quite a unique operating environment that we've tried to create protocols which are quite optimised for. And of course, this realisation that networks are very ordinarily partitioned in these situations. You might have clusters of users who are in contact and then other clusters some distance apart, but there may or may not be a link between them. So delay tolerant networking is a really key piece of that. As I said, fully distributed operation, and of course, there is absolutely no configuration. It should just be install the app, put your name. If you want to try and claim your phone number so that people can find you more easily in a directory kind of setup, that's really all we ask people to do. So all of that is without OpenWRT, because we were trying to do this phone-to-phone directly. But as I say, progress has caused us to have need for external hardware, and we wanted that hardware to be as small and cheap as possible, and to enable many devices to share a single piece of hardware, so that this could still be cost-effective to deploy, but also in these kind of situations, if people needed to build their own mesh extender on the spot, we want that to support as many users as possible. So we want to be as light on the ground as we can. And so sort of our early prototyping ended up with us creating these. This is one of the prototype Serval Mesh Extenders. Inside is a modified TP-Link MR3020 router running an extremely old version of OpenWRT, as it turns out. And it's just been a testament to the flexibility of OpenWRT that we could take this. I think we can buy the routers for like $20 US or so online. We then 3D print a nice case that was designed by our friends from in Slovenia, and we then add a UHF packet radio, which I'll get to in a moment. And so really our motivation around this was this challenge of the increasing difficulty of the communications from peer-to-peer to on phone. What we would love is to make use of the cellular radio in phones, because it's this wonderful broadband, high bandwidth, long range, surprisingly high power, typically up to 4 watt radio that could potentially transfer data at hundreds of megabits over kilometres free line of sight. That would be great. Unfortunately, the chipset varies between every single vendor, and in fact often between operating system builds. The firmware is all locked down. We would never be able, in all likelihood, to get a vendor to give us the support, and then we'd have the whole regulatory problem. For every mobile handset modified, we'd have to get regulatory approval again for every market that it was to be used in, to say yes, this still conforms with the various FCC, EC, Australian or other regulatory requirements. So we've really quite discounted that. If someone has a fantastic silver bullet solution to that problem, please come and tell me, and I'll be glad to buy you a drink. So the next one down then was using the Wi-Fi, which is what we set out to do initially. As I said, that's really been prevented in use in modern versions of Android. Somewhat ironically, iOS has a sort of half-hearted ad hoc Wi-Fi mode that's available. It's a combination of Wi-Fi and Bluetooth. And so this is quite strange, but it's still really not ideal. We can also use Bluetooth on Android and potentially coordinate that with Wi-Fi hotspot mode and Wi-Fi client mode and kind of do all these crazy things. And we have sort of some prototypes of Bluetooth working, but who here has tried to get Bluetooth interoperability working in any app on Android? None of you. Congratulations, that is the correct choice and the correct answer. Don't try, because it will just cause you hurt and pain. And so there's all of these problems have pushed us to external hardware, but in fact the other really key reason that we realised that this hardware was a good idea is if this is running an access point, this can suffer the increased power consumption, not the mobile phone that everyone is carrying. Because of course, there's the nice power-saving features in being a Wi-Fi access point client, where you can do the scheduling and all of this kind of nice stuff. So the need to minimise power consumption, and again, in a disaster zone where the difficulty of getting charge back into your phone is tremendous, this is a key consideration. So this is really what set us going on there. So as I say, so it has a Wi-Fi access point, so we can have short range, high speed, and this is what, it's that Wi-Fi access point that all of the phones would connect to. What's really interesting is that 2.4 gig Wi-Fi in urban areas during peacetime is really quite horrible. But the testbed that we have in the Australian Outback, we can often get 300 to 500 metres out of Wi-Fi because the noise floor is minus 99 dB at 2.4 gigahertz. It's just glorious. We can get 55 dB link margins on a pair of nano beams over several kilometres on 5 gigahertz. There's no water in the air, there's no microwave ovens, it's just fantastic. And so, this happens to some extent in disaster situations as well. So the performance actually goes up rather than down when it's needed most. Then of course we have the ad hoc Wi-Fi. So if you have more than one of these will mesh autonomously and automatically to one another. and they'll do that by Wi-Fi if they're near enough. If they're not, we fall back to the packet radio, which is actually what the antenna here is. So we currently have a 900 meg UHF packet radio suitable for Australia, the US, New Zealand, Canada, Singapore, South Africa, Israel, and just a slightly random list of countries around the world. We can unplug that radio module and put an 868 megahertz version in that would work in Europe and much of Africa and other parts of the world. But our whole architecture is actually radio agnostic, so we can actually use any radio that will let us send and receive blobs of bytes. So that can get thousands of metres in an urban area up to, well, I think the record reported on the RFD 900 is 80 kilometres, but that has some asterisks after it, including that one of the antennas was on a model aircraft, which is what the radios are designed for. So if you want to talk about clear Fresnel zones and low interference environments, think Australian Outback with an aircraft up in the air in clear blue skies. So realistically, we can get about 4 kilometres, with these units sort of 2 or 3 metres off the ground. I think one test we actually did in Massachusetts in the US, near MIT, we put one of these up just on the cupboard in a hotel room, up on the 5th or 6th floor of a hotel. And we could actually walk all around the block and around the next block, and we could actually walk across the bridge on the Charles River to the other side and still get packets being transferred. So the potential is actually really quite interesting for these kind of urban area networks. But if that's not enough, then we can actually use VHF or HF. And so we've actually been doing some testing just recently with Codan and Barrett HF radios. So potentially there's hundreds to thousands of kilometre links between clusters of nodes, but at data rates down to 1 byte per second. But again, we've designed our protocols to handle low data rates. So not ideal, but it can still work. So the software architecture then, of course, we start with OpenWRT. We're using Atheros 9K chipsets because they're cheap, but more importantly, they can do ad hoc and access point simultaneously. So if there's a newer chipset that's nice and cheap that can do that, I'd love to hear from folks as to what a nice step up would be to get a little bit better performance or even better power consumption than we currently have. Then on top of that, the Serval DNA core runs, which was designed from the outset to be extremely portable, because we wanted it to run on Android phones, we wanted it to run on Symbian S60 phones, S40 phones, and so running it on a machine that has 32 meg of RAM in one of these is actually quite comfortable. 16 meg of RAM is typically all we need, often down to 8. Then on top of that, we have the Serval LBARD, which is our low bandwidth interface for supporting the UHF radios, the HF radios, whatever else, and it's quite easy to add additional radio types. So adding on the HF radios, 2 different vendors of HF radios, and adding the crazy parsers for their command line interface took about 24 hours. So this is quite easy to add on. And then finally, we have the sort of onboard web server and, the don't panic screen of how to use the Serval Mesh and the option to download the app onto your phone and some functionality if your phone can't or you don't want to run our app on the phone. So I've already mentioned a little bit that we do a lot of testing up in the Australian Outback. So if anyone wants a nice trip to the Outback sometime, give me a buzz. We have a vehicle supplied, so it's a one-day drive up to Arkaroola, and it's fantastic. And you can do all sorts of fun things at minus 99 dB noise floor. So we have fixed units around on buildings. We also have a number of units on vehicles. And this is kind of where we do the main part of our testing. But what we also have coming up, we're quite fortunate we have some funding from the Australian government to run a pilot in the Pacific, where the idea is to connect communities in clusters on different islands in some of these Pacific nations where communications is perhaps on the main islands but not on outlying islands, and when cyclones and things wipe through, then things are pretty bad. What's really interesting is that in large developed markets, the carriers are, shall we say, not interested in this kind of technology. In these smaller markets where infrastructure, they know firsthand the fragility of infrastructure, they're actually quite supportive. So we're actually trying to work and have some quite encouraging discussions with Digicel in the area there, which has been really cool. We continue to work with New Zealand Red Cross and the UN World Food Programme. Oddly have been the group in the UN who have received the mantle for providing communications as relief within the UN system. Because they already kind of deliver food and blankets and do all the other things, they're already kind of there. And they started to do a little bit of this a few years back, and so they've now kind of been given that mandate. And so we're working with them with their communications within communities program to see if we can make Serval meet the needs for them. And of course, trying to work with some of the local community groups to get this, we want the benefits for this to flow to all members of community, not just a privileged few. And so that pilot will probably be of the order of 50 to 100 units of these, but they won't look like this. I'll show you some images of what we hope that they'll look like in a moment, and some hundreds of Android phones. So we know there's a little bit of scaling work that we need to do with our protocols to get to that point, but the nice thing is delay-tolerant routing makes this a little bit easier. Okay, so this prototype here, as I said, is already just running on a TP-Link board that we've just bought online for $20. The bane of our existence is putting the bulk storage on USB. We wanted the box to be quite small, so if you want the ports to be in the bottom, the USB memory stick comes out on the side, so we have to use the low-profile USB memory sticks. When we started, there were only 2 models, and both of them had flawed firmware, and the USB memory stick would go into permanent read-only mode. You could never reformat it, repartition, or anything after sort of 48 hours of running the software. And then add to that the challenges of if the power is suddenly lost, and also actually the power consumption. It turns out that the USB interface consumes about 20% of the power consumption for one of these sitting idle. So it's about 2 watts with a UHF radio bleeping away at about a 10% duty cycle. And so even with that radio, it's still 10 to 20% of the power consumption is actually this blasted USB interface that just causes us pain. And a minor annoyance, of course, the only serial port that we have on the MR3020 board is used up talking to the UHF radio. So this makes debugging the board a little bit more annoying than it otherwise would be. So we're, under the AusAID grant, designing a new version. So any of the folks here use the Good Life AR150 or similar low-cost boards? If you're after a really nice low-cost Atheros 9K board, I think they're now, again, about $20 US, but they have 64 meg of RAM instead of 32, 16 meg of flash instead of 4 meg of flash, and dual Ethernet ports. There's a header for the serial port, so you don't have to kind of like solder onto tiny pads on the board. They're just really nice for these kinds of prototyping and experimenting. And they have a PCB solderable module, which is actually what we're using. We're going to try and get rid of USB by having a GPIO-based bit bashing micro SD interface. I was very happy to see that the Linux kernel has a generic bit bash micro SD interface that we can try and use. We've yet to try and do that. We'll see. We're also adding into the new prototype intrinsic solar panel charger, motor vehicle 12 and 24 volt, as well as USB charging option, and a multi-chemistry battery charger. So you can have, whether it's sealed lead acid, lithium iron phosphate, or if you're unlucky enough to have to use the explosive type of lithium, that you can use that. And part of the need for having the multi-chemistry actually comes down to a point that I'll bring up in a moment, which is we need to be able to, these things to go across international borders during crisis situations without getting held up at the border. And this actually causes some problems. As I said, we'll come back to that. So we'll have the socket for the different radio types, and we can have the means to connect a different radio externally if you want to, so we can do the HF and that kind of thing just by basically plugging a cable into one of these, into the HF radio, and the unit will go, oh, I have a HF radio now, excellent, and we'll start doing its thing. And finally, of course, having it IP66 environmentally rated so that the unit can work both in outback situations and in tropical maritime. So now the fun bit that may cause minor controversy is how we're trying to deal with things, not just, the FCC problem for us is actually a teeny tiny problem. It's unlikely that we're going to need to import large quantities of mesh extenders into the United States following a disaster, because the domestic capacity for disaster response in the US is quite mature for the most part. Our real problem is when you're trying to get this stuff into developing nations and other disadvantaged nations where everything and everyone is under stress because of what has occurred. So for example, with our friends in New Zealand Red Cross, they were trying to get HF repeaters for the handheld, not HF, VHF repeaters in for the handheld radios for Red Cross to use around the place. And one antenna cable joiner they had happened to be the same part that you could use if you wanted to join a cellular base station to a cellular transmitter infrastructure. Because of that, the whole thing basically got held up in customs for 3 weeks, basically the entire duration of the disaster response, because the customs officials were worried that this thing could be used to cause interference to a cellular network. Now, it's totally absurd, of course, right? We're talking about a small piece of metal that takes antenna A on one side, antenna B on the other side, does no transmission whatsoever itself. But as we know that some of these regulatory concerns are not necessarily they're not entirely merit-based, shall we say. But all the more so when you're talking about a stressed customs official who perhaps hasn't slept for 24 hours, who's trying to get equipment into the country for everyone, but make sure that no problems get caused for the remaining bit of infrastructure that's there for communications. You need to avoid all of these kind of things. So I think next time they try and take one in, they'll actually take it out of its original new packaging and they'll put it in a separate thing that just says, this is a New Zealand Red Cross VHF repeater antenna adapter, not suitable for use on cellular networks. And it will probably go straight through in 5 minutes. But so for us, this is one of the challenges we have to face. We also have to face the fact that we have no money. So we don't want to have different models of mesh extender for different countries because that's just totally untenable for us to do. So what we have come up with is the idea of having the power cable will actually be a DB25. So we have lots of pins, and a bunch of those pins will actually ID whether the firmware should be locked to prevent third-party installation if it's being imported into the US. You can, of course, build your own cable to replace it once you're in the US if you have a legitimate need to change the firmware on it. And it can also encode to tell the UHF radio which frequencies it's allowed to operate on and perhaps which Wi-Fi channels. So the cable will be the only thing which differs. This can be easily soldered. You could make a breakout cable that has all of the options that you need. So this isn't perfect, but we think it will let us get things past the border when they need to. But let's get on to the new hardware. It's not cheap to do. We're spending, I think, of the order of 100,000 Australian dollars, so about 60 or 70,000 euros, to do a bare bones PCB redesign and get the injection molded tooling and all of these things built up. And then there's the certification process and things. So we're still very happy to have help from folks. So here is one side of the new PCB. So the big grey rectangle is the GL-AR150 module. The two Ethernet connectors are in funny places on the board because by default they're not exposed to the outside so as to not breach the weather conditioning. If you want to drill holes in and have Ethernet cables out, that's up to the end user. There's the other side. We're having provision for a super cap so that if the power is pulled suddenly, we can try and shut the thing down cleanly. The black box in the middle is a micro SD adapter, 25-pin connector at the top for power, solar panel and radio configuration. IoT support at the bottom, although really it's mesh of things. And here's our current look at the enclosure on the outside. So there's 3 antenna jacks, 2 bezels as well to put a sunshade on it, and it's curved at the back so you can strap it to a tree or a pole with cable tie quite easily. And then of course at the bottom we have the power and utility connectors and a couple of breather holes so that the thing doesn't implode or explode or pull wet air in a tropical environment. So that's really our adventure to this point. You can dig us up there, and if anyone has any questions now or wants to grab me later or by email, then that would be of course very welcome as well. Thank you.